Hello and welcome. Let's continue with our lecture on mathematical methods. Today I am going to cover integration of complex function over a given curve. This is part of course PH3103 at IISER Calcutta. Let's continue with the lecture. Before getting an idea of integrating complex function, let's quickly get into a short topic, what is called point at infinity. It's an interesting idea used in the complex plane to represent a single point as an infinity. In a complex plane, two-dimensional plane, there are infinite number of infinities, but all these mapped into a single point, what is called the point of infinity. It is an interesting construction provided by Riemann, and that is called the Riemann sphere, and that helps us to map infinity to the single point. Let's first ask a question. Can a sphere be mapped onto a plane? I believe you are all familiar with this, and I am not going into full mathematical detail. I assume that you are familiar that a sphere cannot be mapped onto a plane in a one-to-one fashion. That means sphere geometry is never going to be equal to a plane. It is well understood, and we can otherwise also visualize as a sphere is represented by S cross S, or the outer product of two circles. On the other hand, the plane given as a R cross R or S cross R, we cannot be mapped to a sphere. Now, it is also known if you remove one single point from a sphere, and that can be one-to-one mapped onto a plane. It is also known that if you ignore one point, you can easily map sphere onto a plane, and there are many mappings which are possible. Each will have some shortcoming or some other shortcoming, because this is an idea being well explored by the map makers who need to carry a map on a sheet of paper rather than carrying map on a sphere. Especially sailors, if you have to carry a large sphere with sufficient resolution, it is extremely difficult. So the papers are rather preferred. Even in the couple of centuries back, there are people who believe that Earth is spherical. Of course, if you are a believer of a flat Earth model, then there is no need to worry. With the mapping, each one is fine-tuned for definite utility, and there are artifacts which are pushed outside your region of interest. One of the common example for artifact produced in the mapping onto a plane is the size of Greenland, which looks unusually large for a small island due to the mapping. It also looks that the North Pole or South Pole sometime spread over all the north region. It is one more artifact. So to understand one of the projection, that is called the stereographic projection, which often preserves the angle but not distance between the 2 points, which is used in constructing the Riemann sphere. Take a quick look at the one-dimensional mapping, and then we go to the two-dimensional map. So let's look at the stereographic projection. This is a projection which is used to map a sphere onto a plane. Let's first look at the one-dimensional case where you have a circle being mapped onto R1. So let's take a straight line which represents the R1, and then let's take the origin at x is equal to 0, and then we plot a line orthogonal to that, and at a distance 1 you keep a circle of a radius 1, or you could always call it a and put it at some distance so that the lower pole of this circle touches at x is equal to 0. And then you can have any points on the sphere which is represented by r is equal to 1. It's a unit sphere, and with an angle theta which is measured from the line join meeting at x is equal to 0. This is a normal convention of measuring the theta angle onto the 2D sphere, not so much 1D sphere. So we will easily able to generalize this to 2 dimension. Let's see the theta is equal to 0 corresponds to North Pole, and theta is equal to pi corresponds to South Pole, which map to x is equal to 0. So that is a basic geometry what we have. then the mapping is essentially done through joining a line from point theta on the sphere to theta is equal to 0. So this line which cuts the point on the sphere, and then it joins at the point x. So this map r is equal to 1, theta is equal to theta is a map to x on the straight line. Now the idea is that this map is what we call a stereographic projection. It usually does not preserve the distance between the 2 points. So for example, if you take another point here and then you take a line, and you can clearly see that this distance is not actually corresponds to the distance on the straight line, and that is why it does not preserve the distance. Let's look at the definition. Let's call it a capital phi as an angle made by the straight line joining from north pole to your point which you want to map onto the straight line, and that capital phi can be simply calculated, and based on the simple geometry you can show that the tan capital phi is equal to sine theta into 1 minus cos theta. Now what we have can easily see that when theta is 0, the tan phi goes to infinity, that is a point on the north pole actually mapped to infinity. Theta is equal to pi is already mapped to x is equal to 0. And when theta is equal to pi, tan phi goes to 0, and that is what we have. So this way we can construct, and from this geometry you can easily calculate that x is equal to 2 tan theta, because this distance is equal to 2 because it's a unit sphere. So you can transform this, and we can see that the theta is equal to 0 maps to x is equal to plus infinity, and theta is equal to 2 pi maps to x is equal to infinity. So this way we can bring in infinity to closer in the straight line. So this idea can be easily extended to two-dimensional. We can use a stereographic projection in 2 dimension. Idea is exactly similar. Here you have a S2 and then mapped onto R2, which is a plane. S2 is a sphere, and then basically you do the line connecting north pole and south pole. At the south pole it touches x is equal to 0, y is equal to 0, but we use a polar coordinate. We say that the south pole touch at rho is equal to 0, because if we use the polar coordinate we are going to use rho and phi coordinate system, and then you have your south pole touching origin of a plane. So now we can go do the point on the north pole, and then we draw a straight line and then hit it to the point where you have r is equal to 1, theta and phi. Now it is a two-dimensional. You need two number to represent point on the sphere, that is 2 angle theta and phi, and that mapped onto the plane in a place rho and phi, because we retain the angle phi, which is simply a projection. When we take a point on the north pole and take a straight line, when it is hit, all the point on this circle will have a same value of theta, but phi going from 0 to 2 pi. So that is the entire circle which can be mapped onto the plane by plane polar coordinate. You have a rho and phi. All the points on the phi is mapped to phi itself, but theta is essentially mapped as distance rho, and we can go ahead and calculate. We can call this angle as a capital phi, and that is given by sine theta by 1 minus cos theta, and then rho in this case is given by 2 tan theta. Now we can see that it is a mapping which is done when theta goes to 0. The entire circle goes to infinity, rho becomes infinity, and pi goes from 0 to 2 pi. So this is the idea of infinity. What we have a infinity which is rho is equal to infinity, and all the angle 0 to 2 pi which defines the infinity. Unlike in one dimensional, you have plus infinity and minus infinity. Here the infinity is represented by one dimensional circle with the rho is equal to infinity. Now our mapping onto infinity, it means that it is an inverse. You take a circle with the rho is equal to infinity and phi going from 0 to 2 pi. Using this mapping, you can essentially project it back to here on the north pole, or theta is equal to 0. The entire circle of infinity which maps into a single point, and that point is what we call is a point at infinity. Usually entire circle is represented by single point. It is not uncommon. If you look at the polar coordinate, you have a rho going to 0, phi going from 0 to 2 pi. All of them have a same point as rho goes to 0. It is the same way it happens when rho goes to infinity here, theta goes to 0 and phi goes from 0 to 2 pi. So north pole becomes infinity and the south pole becomes 0, which has a similar sort of a coordinate singularity. But this is an extremely interesting concept which was constructed by Riemann, and it is called the point at infinity, which is very useful if you want to do any calculation, especially integral and other things at infinity. Let us continue with our integral. We need some basic idea of contours and curves over which the integral is performed. Let's first quickly get over the definition of curves. Curves are a continuous function x of t and y of t mapping onto complex plane. Z of t is equal to x of t plus y of t, real variable t, which takes the value from a to b in a closed interval. In a straightforward way, curve is mapping real interval into a complex plane with the parameter t, which starts from a value of a and then goes all over to the value of b. Let's continue with that. Curves can be further classify the curves based on some of its property. A curve is called simple curve if at any point t1 z of t1 is not equal to z of t2 any other point if t1 is not equal to t except beginning or end. So beginning or end can be same, that is called the closed curve or contour. Any other point the curve should not cut itself. That is what it basically says with this complex definition. If you look at this curve at any point it does not cross itself, that is z of t1 is never equal to z of t2, neither z of a is not equal to z of b. On the other hand, you can have an example where a curve cutting itself at several points, and then you will see that these are not simple curve. All these points marked as a cross where your curve is cutting itself, and then that makes it is not a simple curve. Now a closed contour is another definition, which a curve or contour is called closed if beginning point and end point meet each other, or z of a is equal to z of b. Simple closed curve is where it doesn't touch itself anywhere else other than beginning and end point meeting each other. That is called the simple closed contour. Now we are going to start integral of a complex function. The integral of a complex function f of z is defined over a contour C. Now let's get definition of complex integral. The complex integral of a function f of z is defined on a contour C. Let C be a simple contour, and we divide C the small interval reasonably close to each other and name them z0, z1, z2 and zn, etc. They don't have to be equi-spaced, but say that the delta z0 distance between z1 and z0 and so on, we can have a delta zi, and then let's take point in between these z0 and z1, and you have the value of that function f of z0 prime, f of z1 prime, z2 prime, etc. And then the integral is defined as integral f of z dz as a limit delta z going to 0, k going from 0 to n, f of z prime k delta z k. As a limit z goes to 0, this tends to have a unique value, and that is what we call is a integral of function, and this is defined only if the limit exists over the contour. Now if this limit exists, then f of z is said to be the integral on the curve C. Real function of two variable x and y. We have a single value of function defined for given x and y. In the case of complex function, it is actually two functions for a given x and y, that is u of xy and I times v of xy, which defines the complex function. And then delta z also have the same property, that it is a delta x plus I delta y. And when we evaluate integral, we usually can write it and separate the real and imaginary part, and we have a real part as a u into delta x minus v into delta y, and the imaginary part v into delta x plus u into delta y. So you can already see that the property of a differentiability or Cauchy-Riemann condition is going to pop up somewhere, because you can already see the same combination is coming. Later see how the Cauchy-Riemann condition is going to come in the integration of complex functions. That you can have an integration over the closed contour. Usually it is represented by integral over this round defined with an arrow, and the contour is C, and f of z is z. Now you can have a difference between the contour taken along the clockwise or anti-clockwise. Then you have to represent by your arrow indicating how the curve propagate clockwise or anti-clockwise. You know that if you interchange the limits of the integration, there is going to be a sign, and the similar thing is going to appear in the complex number. That is why the orientation of your contour, even in the closed contour, plays an important role in evaluating the integral. Of course, definition is fine. There has to be some practical way of evaluating the contour integral. Let's get to that. Let f of z is a function which is smooth on a curve C, given by parameterization z of t is equal to x of t plus I into y of t for t going between a and b. So this is a basic definition we require for doing the integration. We need a curve and a function. So we evaluate the function f of z dz, and that can be change the variable. Simple chain rule we can use, the change the variable, and it can be redefined. Instead of a dz, we can replace by dt using the simple chain rule, and that is one of the practical way of evaluating the complex integral over a curve, because curve is always parameterized by a real parameter t, and one can use it to integrate over your contour, and that is the simplest way of doing integral. Let's quickly look at an example where we evaluate the contour integral of a function f of z is equal to z star on a closed curve C, given by x is equal to 3t and y is equal to t square. So these two represents the curve where you have a x is given by 3t, y is given by t square. You can basically find out the orbit, but you know that how the curve is given by x of t and y of t. That is what defines your curve. So in this case, x is given 3t and y is given as a t square, where t goes from minus 1 to plus 4. Now the evaluation of integral is fairly straightforward. We have to evaluate our z is equal to 3t plus t square, and we can simply substitute for f of z, that is z star, and then we have a z is equal to 3t plus it square. Z prime is equal to 3 plus 2it. Then we integrate over the contour given here, t going from minus 1 to plus 4, and then integral is basically evaluated from minus 1 to plus 4. You substitute the function z star in terms of t, and then you have a dz in terms of dt and the differential, and then you can simply evaluate this integral. We pushed it little upwards, and then you see that integral is given by this. We expand this. We have a real part and an imaginary part. Each of them is a polynomial which can be easily integrated over a given value minus 4 to plus 4. It's straightforward. You can integrate this to be t to the power 4, and then t as a t square, there is half on the both sides, and then you have a t square there, that becomes t cube, there is already 3 here, and then evaluate the integral from value -1 to +4, and then the value of the integral is 195 plus I into 65. So this is a way of doing the complex integral. We can take another simple integral to show that another technique which is commonly used in evaluating the integral. Let us evaluate the integral f of z is equal to 1 by z, and contour c is given by unit circle. Unit circle in this case is parameterized by x is equal to cos t, y is equal to sin t. It is easy to show that the orbit x square plus y square is equal to 1, and then the parameter which goes from 0 to 2 pi. Now the first thing to do is substitute z is equal to cos t plus I sin t. It can be simply written as e to the power I t, and z prime is I into e power I t. This is one of the simplification occurs if you use unit circle, or for that matter any other circle. You can simply write that curve as a r e power I t, where t going from 0 to 2 pi, and the radius is r, in this case is 1. Now the function also can be easily simplified. You have a 1 by z, which is represented as e power minus I t, and the product is e power minus I t into e power I t. We have I coming from the dz, and then dt going from 0 to 2 pi. These two get cancels out, and what you have is 0 to 2 pi dt, and then the integral is 2 pi I. So this we can easily see that there is a singularity at z is equal to 0, but it is not on the curve which we are taking. The curve is a circle with the unit circle r is equal to 1, theta to 2 pi, but singularity is at center. That does not affect the integral. We can evaluate even if there is a singular point. It takes the value of a finite number 2 pi I. Have an homework. That homework is evaluate a integral over a contour C 8x square minus iy dz, where C is a straight line, y is equal to f of x, where x going from 0 to 2 pi. So in this curve, we don't have an extra parameter. X itself is used as a parameter for the curve, and that goes from 0 to 2, and then the curve is given by y is equal to 5x, which need to evaluate this and upload it on the VLearn.